Hello, this is Mr. P, and today we're going to learn about using trigonometric identities. And we're going to use them both algebraically and geometrically. We're going to use them to evaluate functions, to simplify expressions, to verify identities, and we're even going to do a little bit of factoring as well. We're going to start with the reciprocal identities. The important thing here is to know how they match up, which ones are reciprocals of which ones. For example, sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals of each other. And tangent and cotangent are reciprocals of each other. Now, if you're having trouble remembering how they match up, then if you do remember your SOHCAHTOA, there's a nice little way that one of my students came up with. Here you can add to the SOHCAHTOA to see that sine is related to cosecant, cosine is related to secant, and tangent is related to cotangent. And those who apply to the reciprocal properties, that is. In addition to the reciprocal, we also have the quotient identities, which are related. And for these, we have the fact that tangent is sine over cosine, and cotangent is cosine divided by sine. These can become very useful when you want to change your expressions or equations so that you have just sines and cosines. So these are good substitutions for that. That's sometimes a good idea because with sine or cosine you have more identities available to you, so you can have more opportunity to make substitutions. Next we have the Pythagorean identities, and that's there are 3 of them, but as long as you know the first one, as long as you are able to come up with the first one, you can always derive the other 2. And the first one, more than memorizing it, you should really know that one. You should understand the geometry of the first one. So let's take a look at the geometry of it. We have sine squared plus cosine squared equals 1. Well, if we think in the first quadrant, we're going to take a triangle in the unit circle, so our radius is 1. And if we're in the unit circle, then by definition, the length of the segment opposite your angle theta, this would be our angle theta, the length of that segment is the sine of theta, or sine comes from the Latin word sinus, which means opening, and the length of this segment measures the opening of this angle, as calculated from the terminal point where your terminal side intersects with your unit circle. You drop a perpendicular, and that, distance in geometry means perpendicular distance. So the length of the segment, by definition, is sine. And then if you consider this is our theta, if you consider this angle inside the triangle, this angle would be complementary to our angle theta, because in a right triangle, the two acute angles in a right triangle are complementary, which means they add up to 90 degrees. So this blue segment here would be the opening of this complementary angle. Notice how it has the same hypotenuse, the same radius of 1. So by definition, this length would be the sine of this complementary angle. And we say that that would be the complementary sine, or in other words, cosine. Co means complementary. So by definition, we have this segment is the sine of theta, this segment is the cosine of theta, which means the Pythagorean theorem says the leg squared plus leg squared equals hypotenuse squared, or in other words, sine of theta squared plus cosine of theta squared equals 1 squared, or sine squared plus cosine squared equals 1. Now, once you know the first one, you can easily derive the other 2 by either dividing through by sine squared or dividing through by cosine squared. Let's say you needed cosecant, for example. Then you can get a cosecant by dividing 1 by sine. So here, if I divide through by sine squared, then sine squared over sine squared gives me the 1. Cosine squared divided by sine squared gives me cotangent squared. And 1 divided by sine squared gives me cosecant squared. So you divide through by sine squared, and the first identity becomes the third identity. Likewise, if you divide through by cosine squared, then the first identity will become the second identity. So as long as you know that first one, and you should understand it more than memorize it, as long as you know that first one, you can always derive the other 2. Now, other useful forms of these, if we just manipulate these a little more, we can get some good ways to switch out signs for cosines. For example, if I take the cosine and move it on to the other side of the equal sign, then we'll have a sine squared is equal to 1 minus cosine squared. Or if I wanted to move the sine over to the other side, I would have had cosine squared equals 1 minus sine squared. These are two versions that you will be using a lot of. So you want to recognize the opportunity to make these substitutions. Notice how you can take something that's two terms and substitute for something that's only one term. That can be very helpful when simplifying. Or if you don't need the squares, let's say you needed just sine rather than sine squared, you can take the square root of both sides, but don't forget to add the plus minus. Whenever you take the square root of both sides, you must add the plus minus. And you can do the same for the cosine version, which gives you those two identities. And for similar thought process, you can do the same with the middle identity. We can use this form or this form. And for the last one as well, we can manipulate it. So these other identities are just algebraic manipulations of these three, which are really just algebraic manipulations of this one. All right, next we're going to look at cofunction identities. And remember, there's that word co again. Co means complementary. So as we mentioned here in our diagram, the very definition of cosine means it's the complementary sign or the sign of the complement. Now, a complementary angle are two angles that add up to 90 degrees, or in radians it would be pi over 2. So if you have an angle theta, then the complement of that angle would be 90 minus theta in degrees, or pi over 2 minus theta in radians. So here, this first one literally says that the sine of the complement is equal to the complementary sine of u, or cosine of u. This is the very definition of cosine. And then it also works where the cosine of the complement is equal to the sine, because you have a co of a co gives you back your sine originally. And this same thought process works for tangent. The tangent of the complement is the complementary tangent, and the secant of the complement is the complementary secant. Notice how these are grouped a little differently than the way we group them for the reciprocal identities. For the reciprocal identities, sine was reciprocal of cosecant, cosine was reciprocal of secant, and tangent and cotangent. However, for the cofunction identities, it's all about the word co. You have sine and cosine, tangent and cotangent, secant and cosecant. So you want to make sure you don't mix those two up. And the last set of identities are the even and odd properties. And again, we're going to look at the first two of them here. And the other ones can all be derived from the first two. And these can be very helpful to get a negative sign out of the argument. Remember, the argument is what you're taking the sine or cosine of. So here, the sine of negative u is equal to the negative of sine u. And also the cosine of negative u is equal to the cosine of u. We're going to look at these two algebraically, starting with the first one. And I want you to consider this diagram. Starting with our initial side at the positive x-axis, we're going to open up to an angle theta in both the positive direction, or we're going to open up in the negative direction, the same magnitude. So if we do the positive theta, then I can drop that perpendicular, and now this will work for any triangle, but we're going to assume that we're working inside for simplicity, we're going to assume that this is a unit circle. So our radius is going to be 1, which means that this opposite side is the sine of theta. If it was any other radius, then it would simply be r sine theta, because the radius will act as your scaling factor. So here we have this red segment is the sine of theta, and going in the triangle in quadrant 4, the blue segment is going to be your sine of negative theta. Now we can see that these two triangles are congruent. The bottom was just a reflection of the top one across the x-axis. So these two segments have the same length, but one's in the positive direction, one's in the negative direction. Remember, in our triangles, the legs have a directional component, whereas the hypotenuse is always positive. So the red one here would be a positive value, the blue one would be a negative value, and they would be equal to each other. So the sine of negative theta, which is that blue segment, is the negative of the sine of theta, which is the red segment. Now for our cosine property, again, we're going to look at the same two triangles and realize that the cosine for both of them is that green segment. That is the adjacent side for both triangles. So, of course, it's equal to itself, so it doesn't actually matter whether you go cosine positive theta or cosine negative theta, you're going to get the same value. And this is a very useful property for getting rid of negatives inside of an argument. For example, you could use some of the properties above to change a sine into a cosine, and then use this property to get that negative out of that argument. All right, now all the other four can all be derived from the first two. Of course, sine and cosecant are just reciprocals, cosine and secant are reciprocals, and if you did sine divided by tangent, you're going to get sine divided by cosine, you're going to get tangent. So this value divided by this value is going to give you this value. All right, let's look at a little bit of terminology before we get to our examples. We're going to learn about expressions and versus equations. Now, expressions are numbers, variables, or a combination of numbers and variables. They represent some idea, but they don't have an equal sign, so we can't solve expressions. You're going to see in the upcoming sections that they're going to ask you to do the same thing in many different ways. So you're going to have to be able to read these directions correctly. So with expressions, we can simplify expressions, we can factor expressions, but we can't solve them. This can be simplified though. Notice how the 5's cancel out and 5 goes into 10 twice. So this reduced would be simply x plus 2. So again, you can simplify them, you can factor them, but you can't actually solve expressions. What you can solve are equations. But there are actually two different types of equations we're going to be looking at. First of all, conditional equations are the ones you've been working with all along. Those are ones that are true for certain values of x. So this equation here, 5x plus 10 all over 5 equals 7, that is only true when x equals 5. So that is something you can solve. If x equals 5, then that is true. If x is some other number, then it is not true. Those are conditional equations. And that's opposed to an identity, which is going to be true no matter what the value of x. So here the left side and the right side are really the same expression. We see that the left simplified into the right. Since they're the same expression, it really doesn't matter what the value of x is, it's always going to be true, and that's called an identity. So again, you can't solve the identity, but what you can do is you can verify the identity. And when we verify an identity, we pick one of the two sides and we're going to manipulate it algebraically until we get the other side. What we're not allowed to do is cross over the equal sign. In other words, we cannot add to both sides, we can't subtract from both sides, because to do that uses the algebraic property that is based upon the two sides being equal. You're allowed to add to both sides if both sides are equal. So you can't use the fact that they're equal to prove the fact that they're equal. That would be circular reasoning. So you're not allowed to cross the equal sign when verifying. You can only manipulate one side to look like the other. All right, let's look at some examples here. I'm going to start with this one. They want us to use the value secant of u equals negative 3/2 and tangent u is greater than 0, or in other words, positive, to find the values of all 6 trigonometric functions. All right, so they want sine, cosine, tangent, cosecant, secant, cotangent. Well, right off the bat, from our given, we're given secant, so we can fill that one in right away. Secant of u is negative 3/2. We're 1/6 of the way done, and we haven't even Had to figure anything out. Now tangent is positive, but we don't know what the actual number is, so we'll get back to that. But once we do know secant, we can automatically figure out what cosine is because they are reciprocals. Now, when you reciprocate, you're going to exchange the numerator and denominator, or in other words, flip the fraction over, but you're not going to change the sign. I don't want you to fall into that common trap. Reciprocation has nothing to do with positive or negative. It just means you're flipping the fraction upside down. So negative 3/2, when you reciprocate it, becomes negative 2/3. And once we know these two, then all we really need to know is sine, and then we can figure everything else out. Because cosecant would just be the reciprocal, and once I know sine and cosine, I divide them to get tangent, and then we will be able to get them all. So one of our identities that equated sine to cosine was this one, because I'm looking for sine, not sine squared, so I'm looking for this one. And sine of u is plus or minus the square root of 1 minus cosine squared u. So making the substitution, now that we know cosine, I substitute in negative 2/3 for cosine. When I square that, negative 2/3 squares to be 4/9, so it's 1 minus 4/9, which is 9/9 minus 4/9 is 5/9. And then when you take the square root of a fraction, that's the square root of the numerator over the square root of the denominator. So that's plus or minus the square root of 5 over 3. Now it's at this point where the plus minus is important, because we have to pick one of those. Sine is going to be one or the other depending upon the quadrant it's in. And that's why they gave us the fact that tangent is positive. So if we think about this for a second, since tangent is sine divided by cosine, and that result must be positive, well, cosine's already negative, so that means sine must be negative, because that way a negative divided by a negative is going to be a positive. So of these two possibilities, sine is going to be the negative one. So it's negative square root of 5 over 3, which means once we know that, we can easily find the cosecant. We simply reciprocate. This time, though, we're going to have to rationalize, so don't forget to rationalize. So it's 3 root 5 over 5. And now to find tangent, we're simply going to do sine divided by cosine. And if you want to see the side work, here it is. Remember, when you divide by a fraction, it's the same as multiplying by the reciprocal. Reciprocal of negative 2/3 is negative 3/2. Negative times negative is a positive. And the 3's cancel. And you're left with square root of 5 over 2. And again, once you know that, you can reciprocate to find cotangent. And after rationalizing, you'll get 2 root 5 over 5. All right, let's look at the next example. For this one, they want us to simplify the trigonometric expression. And this might be one of those cases where you're not sure what to do next. And that happens with a lot of these verifying or simplifying problems, because there's more than one way to do it. So as long as you keep your goal in mind, which you want to minimize the number of terms and you want to minimize the number of trig functions, as long as you're working towards your goal, then you should be okay in the long run. And eventually, you can follow a logical approach if you realize that there's only a finite number of things you can actually do to an expression. So once you learn all of those things that you can do to an expression, then you can try them systematically if all else fails. But here, one thing I notice here is I have two terms. This first one is a term and the second one is a term. And if I can change this to a product or get some sort of substitution, then I can maybe get it down to one term. So I do notice that there is a sign in both of the terms. So first thing I'm going to do is factor out that common sign. If I factor that out, then I now get this expression, the sine times cosine squared minus 1. And hopefully you now recognize the inside as one of those, or close to one of those identities that you use. The actual identity is sine squared equals 1 minus cosine squared. But here we have cosine squared minus 1, not 1 minus cosine squared. So a little bit of a algebraic identity here is you can change the order in a difference by factoring a negative sign out. Or in other words, a minus b is equal to the negative of b minus a. So therefore, if I factor that negative out, which gives me negative sine x on the outside, then I can change the order on the inside, and now I have something I can substitute. So 1 minus cosine squared is sine squared. I make that substitution. And then we can do the multiplication here, ending up in our final single term of negative sine cubed of x. And we're done on that one. All right, for our next example, they want us to verify the trigonometric identity. So again, we can't work across the equal sign. We can't like add 1 to both sides. But what we can do is manipulate one side so it looks like the other side. Now, after some experience with these, you'll come to learn that you generally want to choose the more complicated side to work on. I know that sounds a little counterintuitive at first, but mathematically it's easier to cancel stuff out and get rid of stuff than it is to create something that's not there in the first place. So generally you want to choose the more complicated side. So we're going to change the left side to make it look like the right. One thing I noticed right off the bat is the left side we have two terms. It's this fraction plus this fraction. And on the right side we have one term. So I'm going to change my two terms into one term by combining the fractions. And to add fractions you need a common denominator. So on the left I'm going to multiply top and bottom by sine, which would give me sine squared on the top. And on the right, I'm going to multiply top and bottom by 1 minus cosine. So it'll be cosine times 1 minus cosine. And then the common denominator is just the product of the two denominators. So when I combine the two fractions into one fraction, it'll look like this. It looks like it's getting more complicated, but we're going to be able to get some cancellations here. Next, I notice I have a sine squared here. And if I distribute, I will also get a cosine squared. Those are great opportunities for cancellations. So here, if I distribute in the numerator, I will get sine squared plus cosine squared plus cosine. And notice I just changed the order here. I did cosine times cosine is cosine squared, cosine times 1 is cosine. And the denominator, I didn't change anything. I left it in factored form. Now, I put them in that order so that I can group the sine squared and the cosine squared. Because if you remember our Pythagorean identity, then sine squared plus cosine squared is just 1, which means the numerator is really just 1 plus cosine. And you have 1 plus cosine on the top. Now you see why I left it in factored form. On the top and bottom means they can cancel out, which gives you just 1 over sine. And 1 over sine is, of course, cosecant. And now the left side looks like the right side, so we're done with that. Okay, in the next example, we want to factor some trig expressions. We're going to start with some easy factoring. This is just no different than the difference of squares pattern. It is the difference of squares pattern. This would be the exact same thing if it was x squared versus if it was secant squared. Because secant squared is a perfect square, 1 is a perfect square. So we're simply going to follow the pattern of the square root of secant squared is secant. Square root of 1 is 1, so it's secant plus 1, secant minus 1. Just recognize the pattern that you have a difference of squares and follow that pattern. For the other one, we're going to go into a full factorization method showing the factor by grouping just as a review here. It can be done a little faster with trial and error. If you're comfortable with that, that's fine. If not, this will be the full procedure. So here we have a trinomial. We have a squared term, our quadratic term. We have our linear term, and then we have our constant. So this is a trinomial where our a, if we compare it to ax squared plus bx plus c, our a, or our leading coefficient, does not equal 1. So we have to do the a times c, or in other words, the leading coefficient times your constant. So 4 times negative 3 gives me negative 12. And I want factors of negative 12 that add up to the linear constant of positive 1. So I want factors of negative 12 that add up to a positive 1. And that would be 4, and negative 3. Now, since our leading coefficient is not 1, we can't go right to the double bubble. What we're going to do is we're going to use these two values to break up that middle term. So my quadratic and my constant, those don't change. 4 tan squared theta and negative 3, those don't change. But instead of tangent of theta, I'm going to break that up into plus 4 tangent theta and minus 3 tangent theta, like this, using these two numbers to break up that middle term. Then we can use factor by grouping. So I'm going to group the first two terms, and I'm also going to group the second two terms, but I'm not going to write the parentheses down because the third term here is negative. So by not writing the parentheses, that's something I do to remind me to take out the negative of what's common so that we are able to factor this. So looking in the first term, though, or the first group, they have 4 in common and they have a tangent in common, so I can pull out the 4 tangent, which means what remains when you factor something out, that's dividing it out. So what remains, you divide that by 4 tangent and you get tangent. Divide that by 4 tangent, you get 1. And that's factoring out what's common in the first group. In the second group, I'm reminded to factor out the negative of what's common. So 3 is common, so I'm going to factor out a negative 3. And if I do that properly, then what will remain would be tangent plus 1. And if you've done it correctly so far, and if it's factorable, then these two parentheses will be the same. And if they are the same, that also means that they're common, which means they can be factored out. So if I factor out these two parentheses, remember when you factor something out, you create a new parenthesis. So I factor that out to the front, creating a new parenthesis for whatever's left over. And what's left over is the 4 tangent and the minus 3, and that's what goes in the other parenthesis. So that would be our fully factored form. All right, for the next example, we're going to look at, again, another factoring, but this time it's not so easy because these are not the same, or it doesn't start out as easy, because these are not the same function. In order to be able to do what we did in the last problem, we need the same function. So I need to somehow figure a way to switch out a cosecant for a cotangent. And of course I can do that using one of my Pythagorean identities. And in case you forgot which one that was, you should always remember the standard one, which is sine squared plus cosine squared is 1. And you can always derive the one you need. If I need something that has cosecant squared, then cosecant is 1 divided by sine, so you divide through by sine squared. 1 divided by sine squared gives me cosecant squared. Cosine divided by sine gives me cotangent. Sine divided by sine gives me 1. So this is the identity that I want. So instead of cosecant squared, that is, instead of cosecant squared, I'm going to replace it with 1 plus cotangent squared, which gives me that expression. Now everything's in terms of cotangent. I can clean up a little bit more by combining the like terms, combine those constants, negative 3 and a positive 1 combined to be a negative 2. And now I have a trinomial where my leading coefficient is 1. That means I can go right to my double bubble, which is the two parentheses. In order to get cotangent squared, that's cotangent times cotangent. And for the other two, I want factors of negative 2 that add up to a negative 1. And that would be negative 2 and positive 1. And we're done. Make sure that you do change everything to be the same function before you start factoring. All right, for our next example, we're going to simplify a trigonometric expression again. This time, notice we have 3 different functions. And I said before, it usually pays off to change everything to sines and cosines. So I'm going to try that first. Instead of cotangent, I'm going to rewrite that as cosine over sine, which gives me this expression. Now cosine times cosine is cosine squared. And then I have 2 terms here. So if I combine the fractions, I can get 1 term. And remember, sine of t is a fraction because that's the same as sine t over 1. Anything is itself over 1. So if I have sine t over 1, our common denominator would be sine t, so I multiply top and bottom by sine t, which gives me sine squared t. So sine squared t plus this fraction I don't change, cosine squared, and that's all over the common denominator. Now hopefully this jumps out at you as a cancellation opportunity, because sine squared plus cosine squared is 1. So we have 1 over sine t, which is equal to the cosecant of t. So notice how we have an expression with 2 terms and 3 different functions, but with a little manipulation it all becomes 1 term and 1 function. Alright, our next example is they want us to rewrite this expression so that it is not in fractional form. And this is something from Algebra 2 that you're actually going to use in calculus as well with limits. It's a way to either rationalize the denominator or make it those trig functions so that you can use a Pythagorean identity. And the idea here is to multiply by the conjugate. If you have a binomial in the denominator, remember binomial means 2 terms. If you have a binomial expression in the denominator, then you can multiply by the conjugate in order to make that a difference of squares. And in the case of irrational numbers, you can make it rational. So the conjugate of a binomial is simply changing the sign between the 2 terms, and that's sine sign. So 1 plus sine of x, its conjugate would be 1 minus sine of x. So here we have our original expression, 1 over 1 plus sine of x. I want to multiply top and bottom by the conjugate. And the conjugate again is 1 minus sine of x. And it looks like we're making it more complicated at first, but the idea here is we're trying to get the denominator something that we can make a substitution. So 1 plus sine x times 1 minus sine x, that's the pattern for difference of squares. So you end up with 1 minus sine x over 1 minus sine squared of x. And if you remember, 1 minus sine squared of x is cosine squared of x. There's our substitution. And then we can break this up, because we want to get rid of the fact that we have any fractions, so we want to break it up so we can rewrite them. This would become 1 over cosine squared minus sine over cosine squared. Now the first one's easy to rewrite as secant squared. And the second one, we're actually going to break up a little bit differently. And this is not the only way to break it up, but I chose to break it up as 1 over cosine times sine over cosine. So then when I make the substitutions, we already have the secant, and then 1 over cosine is secant, and sine over cosine is tangent. So therefore we end up with this expression, which isn't necessarily a simpler expression, but it doesn't have fractions. So sometimes strategy-wise you need to manipulate something so it doesn't have a fraction. And if you have binomials in the denominator, then the technique you want is to multiply top and bottom by the conjugate. Now, as a side note, notice that I could have decided to make this just sine times 1 over cosine squared. So this would have been the same as cosecant times, sine times secant squared. So this had more than one answer. Alright, in the last example, this is going to be trigonometric substitution. They want us to use the fact that x equals 2 tangent of theta, and the theta is between 0 and pi over 2, in other words, the first quadrant, to write this expression as a trigonometric function of theta. And this is sort of planting the seed for the process you're going to be doing for integration, trigonometric substitution for integration. So we're going to look at the algebra, but then I also want to show you the geometry here. So if we take the expression square root of 4 plus x squared, and the substitution, wherever there's an x, we can replace that with 2 tangent of theta. This can be done completely algebraically, but I want to I want to also relate it to the geometry of it. So here we make that substitution. We have 2 tangent of theta quantity squared. And then when we square that, we get 4 plus 4 tangent squared theta. And the key to trigonometric substitution in calculus is getting these two numbers to be the same. So here we have 4 plus 4, so they're the same number there, which means I can factor that out. So it's 4 times 1 plus tangent squared. And here's my substitution opportunity. So 1 plus tangent squared is secant squared, if you remember your Pythagorean identities. So I get the square root of 4 secant squared. And when I take the square root, I then have 2 secant of theta. Now you might be asking yourself, why don't I have a plus or minus? And that's because right here they told us that theta is between 0 and pi over 2, which makes it in the first quadrant, so that means everything's positive. That's why I did not have the negative one here. So this expression is equal to secant theta. Now another way to approach this would have been to use the geometric interpretation. So if this triangle, we're going to draw a triangle here, if this triangle with our theta is in the first quadrant, then I'm going to draw my triangle like that. And if this is our theta, then in order for x to equal 2 tangent of theta, if we divide both sides by 2 here, that means the tangent of theta equals x over 2. One way that I could draw that, since tangent is opposite over adjacent, is that with respect to this theta, my opposite would be x, and my adjacent would be 2. Once I know that, I can use the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared, and that would give me a hypotenuse of square root of 4 plus x squared. And there's our relationship there. Remember that secant is hypotenuse over adjacent. So if the hypotenuse over the adjacent is that expression over 2, and I wanted just that expression, then I would have to take double that. So that's geometrically why it's equal to 2 secant theta. And with that, we're done with these examples.